Our next chapter focuses on organohalides. We'll start with an introduction. We'll look at naming and classification, bonding, as well as physical properties. We're also going to talk about alcohols because one of the important reactions is the preparation of alkyl halides from alcohols, so we should probably know how to name our alcohols as well. Later in this chapter, we'll be looking at the preparation of organohalides, both from alkanes and from alcohols. Although there are many other ways to make alkyl halides, this is what we'll be starting with this semester. In terms of naming organohalides, we can either use functional class names, which are kind of like common names. So here, something would be named as an alkyl halide, two separate words. Or we can use the substitutive name, which is more of the IUPAC name, and here it's named as a haloalkane. So let's look at a few examples. This is a methyl group and a chloride, so the name of our first compound is methyl chloride. This is an ethyl group and a bromide. Notice these are two separate words. This is a 3-carbon piece, so based on propane, we can call this an isopropyl group. So this compound is isopropyl fluoride. We have 4 carbons in a T, so this is a T-butyl group. We can call this T-butyl iodide. Here, this isn't any common alkyl group, so we don't have a good functional class name for this one. But then one other compound I wanted to mention because we use this in lab. As a functional class name, the CH2 group is referred to as a methylene group, and then chloride. We don't have to say how many chlorines there are because methylene is known to be a CH2, and so then there has to be 2 chlorines. So methylene chloride. For the substitutive names, now we focus on the longest alkyl chain, and then we specify the halogen as a substituent. And so here our carbon chain is 1, so it's methane, and then we have a chlorine substituent on the methane, so this is chloromethane. One word. Here we have ethane with a bromine substituent. We don't have to specify where it is because either location would be carbon 1. So bromoethane. Here we can name this as a 3-carbon piece, so propane with a fluorine at carbon 2. So 2-fluoropropane. We have a 3-carbon group with an iodide substituent at carbon 2 and a methyl substituent at carbon 2. So if we call this 1, 2, 3, this is 2-iodo, 2-methyl propane. For this compound, we didn't have a good functional class name, but we do have an easy substitutive name. 1, 2, 3, 4, 5, 6. So this is 2-chlorohexane. And finally, this solvent that's commonly used in lab as a substitutive name, this would be called dichloromethane. So it's important to be familiar both with the substitutive name and the functional class name for compounds and solvents that are used in lab. In general, the functional class names, these are useful when we're talking about smaller compounds or compounds that have a common alkyl group name, but the substitutive names are going to be better in general because they are more broadly useful. Next, let's take a look at naming alcohols. So once again, we have functional class names and substitutive names. For the functional class names, we can call it an alkyl alcohol. And for the substitutive name, instead of an alkane, we skip the E ending and we name it as an alkanol. So we are naming it as an alcohol. So our first example, we have one carbon and it's an alcohol. So we can call it methyl alcohol, where this is two words, or we can call it methanol. Two carbons, this is ethyl alcohol or ethanol. With three carbons, this is an isopropyl group. So we can call this isopropyl alcohol, or we can call it 2-propanol. We cannot call it isopropanol because that is an inappropriate combination of the common name and the IUPAC name. So this is 2-propanol because it is three carbons, so it has the propane, but it is an alcohol, so it ends with OL, and that alcohol is at carbon 2, so 2-propanol. There have been modifications to the rules, so you can also name this as propan 2-ol. And for a molecule like this, there doesn't really seem to be any advantage going one way or the other. I'm very used to naming it this way, but you might see it this way. And when we get to larger and larger molecules where we have a lot of different substituents, sometimes having the number closer to the term that tells you what substituent we're talking about, that might be more convenient. So just recognize both of them. Over here, we have our T-butyl group, so we can call this T-butyl alcohol, or we can call this 2-methyl 2-propanol. 2-methyl 2-propanol. So it is 2-propanol with a methyl substituent at carbon 2. For our last example, we don't have a good common name for this alkyl group, so there isn't a convenient functional class name, but for a substitutive name, this would be 2-hexanol or hexane 2-ol. So similar to what we saw with alkyl halides, the functional class names will be useful for small alcohols or alcohols with common alkyl groups, but the substitutive names are going to be more broadly useful. All right, now let's get some practice naming both alkyl halides and alcohols. Keep in mind, we focus on 1, 2, 3, 4, 5, 6 carbons, so this would be based on hexane. We number to give our substituent the lowest number possible. So this would be 3-bromohexane. Here we have the same thing. We number from left to right to give the alcohol number 3, but remember we're naming this as an alcohol, so this would be 3-hexanol. In this example, we want to number to give our substituents the lowest numbers, so we're going to start from the right, 1, 2, 3, 4. So this is based on butane. We have an iodo substituent at carbon 1, methyl substituents at carbons 2 and 3. We list our substituents alphabetically, and so this is 1 iodo, 2, 3 dimethyl butane. And remember, when we're listing them alphabetically, we're comparing the I to the M, not to the di. And here, once again, 1, 2, 3, 4. So this will be 2, 3 dash dimethyl 1 butanol, or butane 1-ol. For this compound and this compound, we can conveniently use either the functional class name or the substitutive name. So this can be cyclohexyl chloride or chlorocyclohexane. We don't have to specify a number because any substituent on the ring would automatically be at position 1. Then for our alcohol, this can be called cyclohexyl alcohol or cyclohexanol. So a couple of options. Now, when we look at these compounds, this is where we're going to start to see a difference. Looking at this one, we have a substituent here and here. Halides are equivalent in priority to alkyl groups. So to name this, we are going to number it to give the lowest substituent numbers possible. So if we go from right to left, that gives us our substituents at 2 and 4, whereas if we went from left to right, this would be 3 and 5. We have a 4-bromo, a 2-methyl. We list them alphabetically. So this will be 4-bromo, 2-methyl hexane. If we tried the same thing over here, 1, 2, 3, 4, 5, and 6, this gives us the lowest numbers overall, but because we are naming this as an alcohol, the alcohol has priority over an alkyl group. So we name the compound to give the alcohol the lowest number possible. So right to left, our alcohol is at carbon 4, but if we number left to right, now our alcohol is at carbon 3. So this is the way we want to go, even though that puts our second substituent at carbon 5. So this will be 5-methyl 3-hexanol. So alcohols have priority over alkyl substituents and over halogens. Halogens and alkyl groups have equal priority. Okay, looking at this one, if we number right to left, then we have 2 substituents at carbon 2 and 1 substituent at carbon 3, which is better than 1 substituent at 2 and 2 substituents at 3. So this will be 2-chloro, 2,3-dimethyl butane. And here we want to give the alcohol the lowest number, so 1, 2, 3, 4. So again, we're numbering right to left, just like we did here, but for slightly different reason. So this will be 2,3-dimethyl 2-butanol. And then our last pair of examples. Remember, if we only have one substituent on a ring, we don't have to specify where it is because it's automatically at carbon 1. But if we have 2 substituents, then we do have to specify that they're both at, in this case, carbon 1. So this would be 1-fluoro, 1-methyl, hexane, cyclohexane. And now this one, the alcohol, this is our carbon 1, and because we're naming it as an alcohol, the alcohol is automatically at carbon 1, so we only have to specify where the alkyl group is. So this is 1-methyl cyclohexanol. 1-methyl cyclohexanol. All right, so get some practice going from structure to name and going from name to structure. Now, another really important feature is to classify both alkyl halides and alcohols. And we will classify them as primary, secondary, or tertiary based on how many carbons the carbon that it's connected to is connected to. What the heck does that mean? If we look at this bromine, it's connected to this carbon, and this carbon is connected to 2 carbons. So this is a secondary alkyl halide, right? So because the bromine is connected to this carbon, which is connected to 2 other carbons. This is also a secondary alcohol because the alcohol is connected to this carbon, which is connected to 2 other carbons. Here, our iodine is connected to this carbon, which is connected to one other carbon. So this is primary. This alcohol is also primary. The chlorine is connected to this carbon, which is connected to two other carbons. This is secondary. This alcohol is also secondary. This is secondary. This is also secondary. This is tertiary because the chlorine's connected to this carbon, which is connected to 1, 2, 3 other carbons. This is also tertiary. This is tertiary, and this is tertiary. We can't have a quaternary because that would mean that we would have a substituent connected to a carbon that's connected to 4 other carbons, but that would give a total of 5 bonds to that central carbon. So there's no quaternary, but we can have primary, secondary, or tertiary. It's important to be able to classify both alcohols and alkyl halides as primary, secondary, tertiary because there will be differences in reactivity. All right, now let's talk about the bonding within organohalides. So what holds an alkyl halide molecule together? So let's look at our nice simple compound chloromethane. And if we write this out as the full Lewis structure, this carbon is connected to the 3 hydrogens. Here's the chlorine, and the chlorine has 3 lone pairs. So what we talked about with carbon and also with oxygen and nitrogen, we can do the same thing with chlorine when it comes to hybridization. So with chlorine, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So if we focus on our 3s and 3p, we have 2 electrons in our 3s and we have 5 electrons in our 3p. But the s and the p orbitals can be blended or hybridized to give 4 sp3 hybridized orbitals. Now, if we fill in our electrons, we have 1, 2, 3, 4, 5, 6, and 7. So what this gives us is lone pairs and a bonding electron. So an sp3 hybridized chlorine has 3 lone pairs, which is what we see up here, and it has 1 unpaired electron that is used to form a bond. So both of these are sp3 hybridized. So if we think about the shape, because our carbon is sp3 hybridized, we know it's going to have a tetrahedral arrangement. And so this bond angle, these are all going to be approximately 109.5. If we think about our lone pairs relative to this, these are also going to take on a tetrahedral arrangement, but we kind of don't care because we don't really see it in the same way. So this bond is created by the overlap of a carbon that's sp3 hybridized with a chlorine that is sp3 hybridized. So more specifically, it is the sp3 hybridized orbital of a carbon overlapping with an sp3 hybridized orbital of a chlorine to form this sigma bond. And finally, what holds an alkyl halide molecule together with other molecules? Well, if we think about electronegativity differences, we know that chlorine is more electronegative than carbon, so there is a bond dipole. Once again, thinking about the shape of the molecule, and then let's fill in that bond dipole. Then this leads to a molecular dipole that looks like this. So there is a molecular dipole, which means that the intermolecular forces will be dipole-dipole interactions. However, the dipole is not really that strong, so overall the dipole-dipole interactions are not especially strong. Let's compare some physical properties. Now, we're looking at methanol compared to chloromethane compared to ethane. So normally when we are comparing different types of intramolecular forces, we want to stick with the same or similar molecular weight. We're not doing that in this case, but that's okay. What we're looking at here, these can do hydrogen bonding. So a molecule of methanol is held together to another molecule of methanol by hydrogen bonding. With chloromethane, this is dipole-dipole. And with ethane, we're talking about London dispersion forces. In terms of boiling points, we are looking at 65 degrees Celsius. Even though chloromethane is bigger, it has a much smaller boiling point. And then ethane also has a really small boiling point in comparison. So even though it's a bigger molecule, the dipole-dipole interactions are still weaker than what we have with hydrogen bonding. Also, in terms of solubility, alkyl halides are not very soluble in water. They will be much more soluble in organic solvents, not very soluble in water, because we're thinking about a trade-off for the water molecules from hydrogen bonding to settle for dipole-dipole, and that's not a very good trade. Here is an electrostatic potential map for a methyl halide. And so fluorine, chlorine, bromine, and iodine are all more electronegative than carbon. So we'll have a partial positive on the carbon, a partial negative on the halogen. And if we look at the electrostatic potential map, we have kind of positive character down here and negative character up here because it's blue positive, red negative. And so that's going to be similar for all of the alkyl halides. But the degree of partial positive and partial negative character, that's where there will be some variation. Now let's compare the boiling points within the alkyl halides. If we were to focus on electronegativity differences, we know that fluorine is the most electronegative. So fluorine compared to carbon, we're going to have a big dipole, a little bit smaller for chlorine compared to carbon, smaller for bromine compared to carbon, and even smaller for iodine compared to carbon. So if we think about the bond dipole and how that relates to the possibility of the dipole-dipole interactions, we might expect that fluoroethane has a higher boiling point than these other molecules. But it turns out that for the boiling points, we are looking at a negative 32 compared to 12, 38, and 72. So while the dipole is important, we also need to remember that as the size increases, the polarizability increases. Polarizability increases. So that means that the London dispersion forces become much more prevalent. So this takes care of our introduction to organohalides. It's important to know the basics of naming both alcohols and alkyl halides so that we can actually communicate about them. And it's also helpful to think about structure, both the intramolecular bonding and the intermolecular attractions. And really thinking about this is quite important. Because of the electronegativity differences between carbon and the different halogens, we have a dipole. Now, the dipole doesn't have that much of an impact when it comes to intermolecular forces, but it does have a very big impact in terms of reactivity. And we're going to see a lot of reactions that rely on this difference in electronegativity, because here we have an electrophilic carbon that can be attacked by a nucleophile. So that's some of the reactivity we're going to see in the future.